So there's matter and there's energy. Energy is not matter. Energy is real, but it's not matter. It doesn't occupy space or have mass, but it's a major component of our universe. Scientists generally define energy as the capacity to do work, which means we have to define what work is. Work is the result of a force acting on a distance. So if I take this water bottle and I push it across the bench, I've done work. Did I get a salary for doing that? No, but I did work in the scientific sense. If I pick up this pen, if I pick it up, I have applied a force against the force of gravity, and I've moved it in a distance, and I've done work. So all of you have worked today, right? Walking across the room is work in the scientific definition. Energy is really important in understanding chemistry because the behavior of matter is driven by energy. Energy helps us understand and helps us predict what matter will do. So we need to understand energy so we can understand chemistry. Matter is also conserved, energy is also conserved like matter. And so we have another one of these conservation laws, the law of conservation of energy. Energy is neither created nor destroyed. The total amount of energy is constant. The total amount of energy in the universe is constant. There is not energy being created or destroyed. So we can have energy change from one form to another, and some forms are more useful, but it doesn't change its amount. And we can have energy being transferred from one object to another. But energy cannot be created out of nothing, and it doesn't vanish into nothing. So you cannot have a perpetual motion machine. People used to think they'd made a perpetual motion machine, and the idea was this moves all by itself, and it'll keep going forever without us putting any energy into it. And you could probably harness that and empower the world. Yeah, people would try to get patents and stuff, and if you look into them carefully enough, they all have some hidden or overlooked source of energy. It just isn't possible. There are different forms of energy, and we need to have a general idea of what these different forms are. So there is kinetic energy. Kinetic energy is the energy associated with motion, and potential energy is the energy associated with position or composition. Those two are very important to understand. The total energy of a sample of matter is going to be the kinetic energy plus the potential energy. Kinetic energy has to do with motion. Kinetic energy is 1/2 the mass times the velocity squared. So the faster something is moving, the more kinetic energy it has. And the more mass something has, the more kinetic energy it has. If you had two people running at you at the same speed, and one was a kindergartner and one was an O lineman from the Fresno City football team, and they both ran into you, which one has more energy? The O lineman, right? Now, depending on the guy, maybe he can't run any faster than the kindergartner, but he's got mass, right? When my son played for COS, there was a guy on their team that weighed 400 pounds. And he was like a wall. He was bigger than a refrigerator. He was huge, right? And that guy didn't have to be going very fast to just knock you over. He had kinetic energy because of his mass. Now, velocity matters, the speed at which it's moving. You take two similar objects, maybe a tennis ball, and someone just very lightly throws a tennis ball at you. Does it hurt? Probably not. Give it to the pitcher on the baseball team and have him throw it at you. That's going to hurt. Same amount of mass, higher velocity, more energy. Okay? So that's kinetic energy. Potential energy has to do with either the position of the substance or its composition. So when I was growing up, we watched a lot of cartoons on Saturday morning. And one real common feature of cartoons, they're always moving pianos and anvils, right? And they're hanging out of the second story window, and somebody walks under, and then the rope breaks, and the piano falls on them, right? That piano hanging out of the second story window has potential energy. It's not very stable. And you cut the rope, and it's going to fall. As it falls, its potential energy from its position is converted into kinetic energy of motion. And by the time it hits the poor guy on the sidewalk, it's moving very fast and has a lot of kinetic energy and smashes him. Of course, with the cartoons, 2 seconds later, he pops back into form and he's off chasing whoever it was he was after. Potential energy due to position. Something like gasoline has potential energy due to its composition. Gasoline is very flammable, and so if we provide it the conditions to burn, it will turn that potential energy from its composition into energy that we can use. 2 other kinds of energy. Electrical energy. This is energy associated with the flow of electrical charge, so electrons moving. Thermal energy is a form of kinetic energy. It's the energy associated with the random motions of atoms and molecules in matter. When you heat matter up, when you put energy into it and raise its temperature, the particles move more and more. And so in the solid state, you can imagine if we heat up the solid state of students, which kind of happens as the class goes on, you get more and more fidgety. And you're jiggling your leg, and people are getting antsy, right? And so as you heat up a substance, the molecules are getting antsy. They're not traveling distances, but they're moving more. That thermal energy is a kind of kinetic energy. And then chemical energy is a form of potential energy. And it's associated with the positions of the particles in a chemical system. So in gasoline, the particular arrangement of the carbon and hydrogen atoms is such that it will explode and combust. And other substances don't do that, but it's a potential energy. Well, energy is a quantity that can be measured, and if we can measure something, we have to have some units for it. The SI unit of energy is the joule. The abbreviation is a capital J. It's a French word, but it's pronounced jewel like you would have a jewel in a crown. So that one's important. And calorie is important. I think everybody's heard of calories. But this calorie is not the same as a nutritional calorie. A nutritional calorie is with a capital C, and that's actually 1,000 of these little c calories. So a calorie, a scientific calorie, is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. And we have a relationship here. One calorie is equal to 4.184 joules. So that tells us that the calorie is a larger unit than the joule. Small number, bigger unit, bigger number, smaller unit. They're still in the same ballpark, though. I won't make you memorize this conversion, but you may need it on some homework problems. And so there it is. It's also in your book. If you need it on an exam, I'll provide it in a table or something. The nutritional calorie is 1,000 calories, or 1 kilocalorie. Calories and joules fall into the metric system, and you can use all of those prefixes with them. So a kilojoule is 1,000 joules. And then the electric company measures energy in kilowatt hours. We don't need to know that, though. Skip that part. So here's some useful conversion factors. I suppose the kilowatt hour thing could come up on a homework problem, but I don't think I assigned anything like that. But you just treat it like any other unit, and there's a relationship. So a this is a capital C calorie is the same, good grief, is equal to 1 kilocalorie. Now we have to be careful with our abbreviations here. Don't try to abbreviate that C, because people will misunderstand what you're meaning. And this is a capital J, not a lowercase j. So we can do conversions of energy units, and we're going to use dimensional analysis to do this. We're going to find that dimensional analysis comes back over and over and over again. Just when you think it went away, it's going to come back. And so if you're still struggling with converting units and with that whole idea of dimensional analysis, the sooner you get help with that, the better. So let's look at this. The complete combustion of a small wooden match produces approximately 512 calories of heat. How many kilojoules are produced? Well, this is one of those word problems. What's important in a word problem is generally the numbers. So we have one number in here, 512 calories. So let's write that down, 512 calories. And then what are they asking us to find? Kilojoules. So over here we want to end up with kilojoules. Lowercase k, capital J. The exact path that we take here is going to depend on what conversion factors we know. What conversion factor do we have between calories and joules? 1 calorie equals 4.184 joules. That was given in the slides, right? So you're looking for conversion factors and you find this one. You're like, oh, awesome, I can go from calories to joules. You have to have the conversion factor, this relationship, in order to go from here to here. Can we go from joules to kilojoules? Yes, we can. This is a metric conversion just using prefixes. You could look around, but in your book you're probably not going to find a conversion factor for this because it's the general conversion factor, the same thing that we would use between meters and kilometers. And the relationship there is joule equals joule. I'm going to put the prefix on one side, and I'm going to put its mathematical meaning on the other side, and ta-da, I have my conversion factor. Now we follow the path we set up, 512 calories. I have 2 arrows. I need 2 fractions. And we pretend we're Dora the Explorer. Calories, joules, kilocalories. Calories, joules, kilocalories. Kilojoules, thank you. I was testing you. No, I wasn't. So calorie here, we want it to go away, so we're going to divide by it, because that's how we make things go away using math. I wish we could do that in real life sometimes, but it doesn't work so well. We're going to divide by joules to make it go away. Then we have this relationship. 1 calorie is equal to 4.184 joules. I need to keep the numbers with their units. It's 1 calorie, 4.184 joules. And then this relationship. Here I wrote it out. You can also, once you're comfortable with it, just do it right here. There's the prefix. What does it mean? I want to write what it means on the other side. There are other ways to do metric prefixes and conversions, but this method follows a pattern and will always get you the right answer. And so I'm going to be consistent in using it in lecture. Kilo means 10 to the third. So I put kilo on one side of the fraction line and what it means on the other. Now, how do I get that into my calculator? I just multiply it by 1 and all of a sudden it's in scientific notation. So on my calculator now, which I forgot to get out, I'm going to take 512 and I'm going to multiply by 4.184 and divide by 1 EE3 equals. And how many significant figures should I report in my answer here? 3. This number, has 3. This one has 4. That's not an exact conversion. This is exact, and so I don't have to worry about it. So my answer is going to come out to be 2.14 kilojoules. Any questions? Same process, just some new units.